So in this lecture, we're going to take a look specifically at the isotropic version of generalized Hooke's law and the associated strain energy density function that we're using as a potential function. So previously we had written down that U is equal to 1/2 lambda epsilon 1, epsilon 2, epsilon 3 quantity squared plus G, epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared, where epsilon 1, epsilon 2, and epsilon 3 are principal strains, and G and lambda are the Lemay coefficients. Now, we're going to take a look at the characteristic equation and the invariance of the strain tensor. Previously in our textbook, they had used lambda as the eigenvalues of the strain tensor, but I don't want to confuse that with the Lemay coefficient lambda, so I'm using epsilon sub p. And there's our expression of our characteristic equation with J1, J2, and J3 being the invariance of the strain tensor, which again is another thing we have to watch out for notationally for two reasons. One reason being, in this expression, this definition, I have alternated the signs of these terms in the characteristic equation, in which case J1, J2, and J3 are listed below. Now J1 is the trace of the strain tensor. We can write that in either coordinate strains or principal strains, as shown below. J3 is the determinant of the strain tensor, or in terms of principal strains, epsilon 1, epsilon 2, epsilon 3. And J2, we're going to look at it in more detail. In terms of coordinate strains and index notation, is 1/2 epsilon II, epsilon kk minus epsilon ij, epsilon ij. Now, the other notational issue that we have is that some people call J2 the second invariant of the deviatoric stress tensor and use it in plasticity theory. We got to pick something to call our strain tensor invariance. We're going to call it J2. So don't confuse that with some of our previous discussions on the deviatoric stress tensor. So looking at that J2 term more carefully, we can expand it out, and we get some terms that cancel with the minus sign. So epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3 quantity squared gives us a lot of terms. We have mixed terms in terms of the coordinate strains. And then the minus epsilon ij gives us negative terms, gives us 9 terms, and we can see some of them cancel out. And I've circled the ones that cancel out. We have a half out in front of the entire expression. The terms that are left involve the coordinate strains, the normal strains that look like epsilon 1, 1 and epsilon 2, 2. Okay, they're down here after the half is brought through. And then we have shear terms that are negative, and so we have minus 1/2 these various shear terms. And I'm writing this in a non-symmetric version, but if we change it to a symmetric version, we get the next line below. And then we have an expression for J2 in terms of principal strains. I'm going through this kind of quickly, but this is just tons of algebra. But the reason why we wanted to write J2 in terms of principal strains and coordinate strains is that we can convert our strain energy density function from our principal strains into the invariance of the strain tensor. So the first line is our expression for U. The second line is an equivalent expression. And the middle line with the red bracket over here to the right is the proof that these two first lines are equivalent. And with that, we can write that U is equal to 1/2 lambda plus G, that quantity, times J1 squared minus 2G J2. Now that we have this expression in terms of invariance of the strain tensor, we can rewrite this in terms of coordinate strains. And in terms of coordinate strains, we have our expression for u with the g and the minus 2g. Again, I'm leaving this as a non-symmetric expression. The first term is 1/2 lambda epsilon 1 plus epsilon 2 plus epsilon 3 quantity squared, 1 1 plus 2 2 plus 3 3 quantity squared, plus g times, from the first term, we get epsilon 1 1 plus epsilon 1 1 squared plus epsilon 2 2 squared plus epsilon 3 3 squared. We get some positive 2 times those mixed terms, 1 1 times epsilon 2 2 plus epsilon 1 1 times epsilon 3 3, all that. We get 2 times those kind of terms. But then we're subtracting off some terms minus 2 times epsilon 1 1 and epsilon 2 2. So those products of the normal strains that are not with themselves vanish. If we distribute the minus 2 through, we have a positive epsilon 1 2 and an epsilon 2 1 and so forth in this expression. You might notice that I had erased a few things and had made a little mistake there, and I want to come back and fix it. So I'm just going through that kind of fast. But what I want to do next, and the reason why I wanted to start this over again, is because I want to take the partial derivative of u with respect to epsilon 1 1, because that's what sigma 1 1 is going to be equal to. So let's do that. Now, I have 2 times 1/2 times lambda, which gives me lambda times the stuff in the brackets to the first power. And then the only term that has epsilon 1 1 is this leading term, so I'm going to have a 2g epsilon 1 1. And I have similar expressions for the normal stresses, sigma 2 2 and sigma 3 3. Let's take a look at the shearing stress term, sigma 1 2. It's the partial derivative of u with respect to epsilon 1 2. I get no contribution from the first term because there's no shear terms in that term with lambda in it. On the second term, with respect to epsilon 1 2, I would have a 2 times a g times epsilon 1 2. And this is the entire reason why I like to write this as a non-symmetric expression. Whenever we have a potential function with tensor components in it, a lot of books will compress those terms, and it's pretty hard to figure out exactly how they get their partial derivatives. But if you leave them as non-symmetric, take up a little more space in the book, and it's very easy to see where the partial derivative term comes from. We also get similar terms for sigma 2 3 and sigma 1 3. Now, if we look at these terms all together, we can get an expression for sigma ij. It's equal to lambda times the trace of the strain tensor, which I'm going to call E. But this term only turns on when we have a normal strain, either 1 1 2 2 or 3 3. So in index notation, I'm going to use a Kronecker delta ij. So see, when I have sigma 1 2, this term vanishes. But then I'm going to have a 2g times epsilon ij. And here, little e is the same as what we had previously called j1. It's equal to the trace of the strain tensor. epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3. So what I really want you to get out of this is this expression. Alright, now the rest of this is going to be a lot of manipulations of things. The algebra is fairly tedious. I'm going to present it all and then just kind of talk through it. In my opinion, there's probably not a big reason for anybody to write any of this down if you follow it and it makes sense. I do it because I need to make sure the book's equations are right. And I know they're right, but I wanted to go through the algebra. But what we're going to do next is we're going to invert this and to write this instead of stresses in terms of strains, we're going to rewrite this in terms as strains in terms of stresses. Alright, well let's start with sigma ij, that expression that we had. Now again, I'm rewriting this in a slightly different form. I'm using epsilon kk to indicate the trace, but lambda epsilon kk Kronecker delta ij plus 2g epsilon ij. Well, let's compute the trace of the stress tensor. We had called that I1, and it's the sigma 1, 1 and the sigma 2, 2 and the sigma 3, 3 terms all added together. Well, what are we going to get? We're going to get 3 times the trace of the strain tensor, epsilon kk, plus 2g times the quantity, epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3. Oop, I forgot my lambda. So we're going to have 3 lambda plus 2g times the trace of the strain tensor. And we can even write that in terms of J1 if we want. Now, let's solve for little e. Little e is going to be the trace of the stress tensor divided by 3 lambda plus 2g. Now let's solve for epsilon ij. Epsilon ij is going to be equal to sigma ij over 2g minus lambda Kronecker delta ij times little e and we can rewrite this again if we would like, maybe a little bit more standard format, 1 over 2g sigma ij minus, I lost the term here, I lost my 2g, minus lambda over 2g, 1 over 3 lambda plus 2g times the trace of the stress tensor sigma kk Kronecker delta ij. So it's relatively easy to invert the tensor form of 3D Hooke's law for isotropic materials. Now let's take a look and see how this is related to our more familiar form of 3D Hooke's law. Alright, now you may remember in undergraduate mechanics materials, epsilon x, or epsilon 11, would be sigma 11 over E minus nu sigma 22 over E minus nu sigma 33 over E. And epsilon 12 would be equal to sigma 12, well, divided by 2G. Well, let's see how these things relate to one another with the expression that we have up here. Let's write down from the tensor expression what epsilon 11 is equal to. It's 1 over 2G sigma 11 minus lambda over 2G 1 over 3 lambda plus 2G, the trace of the stress tensor, sigma 11 plus sigma 22 plus sigma 33, and then Kronecker delta ij. Okay, so that term is there because for epsilon 11, Kronecker delta 11 is equal to 1. Now we do have terms like epsilon 12. Remember, these are tensor strain components, not engineering shearing strain components, gamma. So these are tensorial shearing strain components. They're half as much as the gamma engineering shearing strain. So epsilon 12 is equal to 1 over 2G sigma 12, and this term goes away because it just doesn't exist. So we have perfect agreement with our shearing terms, and similar for epsilon 13 and epsilon 23. But let's see what's going on with this term for the normal strains. And I'm going to take this top equation, I'm going to write it one more time down here. I'm going to have epsilon 11 is equal to a sigma 11 over E minus nu over E sigma 22 plus sigma 33. In this term, I'm going to rewrite, I'm going to collect terms together. My first term is 1 over 2G minus lambda over 2G 1 over 3 lambda plus 2G times sigma 11. And then I'm going to have a minus lambda over 2G 1 over 3 lambda plus 2G times sigma 22 plus sigma 33. Now, the reason why I wanted to do that is because now we can equate coefficients. The coefficient of the sigma 11 term is this one right here, and the coefficient of the sigma 22 plus sigma 33, this term is this expression right here. So 1 over E is equal to 1 over 2G minus lambda over 2G times 1 over 3 lambda plus 2G, and nu over E is equal to lambda over 2G 1 plus 3 lambda plus 2G. With that, we're going to do two things. We're going to solve for nu and E in terms of the Lemay coefficients, and then we're going to invert them and solve for E and nu in terms of the Lemay coefficients, or vice versa. We're going to solve for the Lemay coefficients in terms of E and nu. I think I said the same thing twice. Get a little punchy at the moment. Alright, so let's start. I'll write down those equations again, and probably I'll just have a page that I'll pop up and let you look at the algebra. Okay, so there's my first line. 1 over E is equal to that expression that we had written on the previous page. Finding a common denominator And simplifying leads to 1 over E is equal to lambda plus G divided by G times 3 lambda plus 2G. Now the expression nu over E is what we had on the previous page, is lambda over 2G times 1 over 3 lambda plus 2G. If we solve for Poisson's ratio nu, we get lambda over 2G times 1 over 3 lambda plus 2G times E, which is G times 3 lambda plus 2G divided by lambda plus G. Canceling out the common terms, we're left with Poisson's ratio nu is equal to lambda divided by 2 times lambda plus G, and the modulus of elasticity E is equal to G times 3 lambda plus 2G divided by lambda plus G. So here we have familiar elastic constants in terms of Lemay coefficients. And this is for an isotropic material. Now we're going to also use this expression a little bit later. So I just want you to keep that in mind as we look through the next pages. In my opinion, this isn't something anybody's going to want to memorize. But this is just the algebra to show how these things are related to one another. We can do some algebra to solve for Lemay's coefficient, lambda, in terms of G and nu. Now G is a Lemay coefficient, but as we talked about for an isotropic material, there's also the shear modulus, the familiar shear modulus. So lambda is equal to 2 nu G divided by 1 minus 2 nu. You see the algebra there. I won't talk through it. But we're going to take that expression for lambda and put it into our expression for E. You go ahead and write that down. We'll get that started. So E is equal to G times this expression, 3 lambda plus 2G divided by lambda plus G. All right, let me start with that for the next page. All right, so we can work with that with the modulus of elasticity E, written in terms of G and the Lemay coefficient, but now we're writing Lemay coefficient in terms of Poisson's ratio and G. We can go through the algebra and we finally get that G is equal to E over 2 divided by 1 plus nu, which should be a very familiar expression for isotropic materials. Furthermore, since lambda is equal to 2 nu G over 1 minus 2 nu, we can do a little bit more algebra. And find that the Lemay coefficient lambda is equal to nu E divided by 1 plus nu times 1 minus 2 nu. So now we have G and lambda in terms of E and nu, and we saw previously that we can write E and nu in terms of G and lambda and invert these back and forth and all over. Now, what do I want you to get out of all of this? Is that Hooke's law for isotropic materials can be written as sigma ij is equal to lambda epsilon kk Kronecker delta ij plus 2g epsilon ij, and epsilon ij can be written as minus nu over e sigma kk Kronecker delta ij. Remember, this is the thing I asked you to recall in a couple pages, plus 1 plus nu over e sigma ij if it needs to be inverted. Now, some people, some books, use mu instead of g. So up here, that can also be written as sigma ij is equal to lambda epsilon kk Kronecker delta ij plus 2 mu epsilon ij. So you might see it look like that. Now, we've done a lot of algebra in these pages, but yet still we have this tensor form. So at this point in the course, you should be very familiar now with index notation, and that shouldn't be an impediment. So you should know what epsilon kk means, you should know what Kronecker delta ij means, and everything else. But here we have Hooke's law in terms of Lemay coefficients, and or we can write it in terms of E and nu.